Hey everybody, I'm going to do a recap. So I put the cover back on our furnace. So now we have sealed combustion. So remember, when this comes on, when our draft inducer comes on, it's pulling a negative pressure on our heat exchanger and all the way up through our burners. And since this is on there, like, it can't pull from the area that I'm standing. It can't, like, this is blocked off. It's sealed. It's called sealed combustion. So it can only pull from this white pipe because this is connected to this smoke box. So that negative pressure is drawn through this, and then eventually that goes outside. And we're going to learn all about that pipe coming up in the future, probably when you come back to class. I can't wait. Can't wait till everybody comes back to class. So, but in the meantime, I will be doing videos showing you what you would normally be doing in class. And then my goal, when we all come back and we're all face to face with masks on, we get to do this ourselves. So watch the videos, learn some stuff, and then I'm hoping that, like, in a couple of lab periods we can blast through everything that we missed, and it would be like you didn't even miss anything. So right now I'm going to work on the draft inducer. So we already know what it does, what its function is, right? It induces draft. Like that, those flames wouldn't be drawn into that heat exchanger and drawn through and exhausted out if this wasn't here. Fire wants to go straight up. It doesn't want to get pulled horizontally and down. So that's why we have this, okay? If this wasn't pulling a suction on all of that, none of that would happen. So it's an electric motor. And I've got one that I took apart. There's a bunch of screws that hold it together. And as you can see, like, I've already pre-removed these screws. If I look at this, it's a centrifugal fan. I take this apart and it looks like this. And so this is the inlet of the fan right here, and this is the outlet of the fan. So this part is the part that's drawing the negative pressure through our heat exchangers, across our burners, and eventually through this pipe from outside. It's drawing outside air in for combustion, using the air, the oxygen from that air in the combustion process, and then it eventually exhausted out this pipe. So this, it's like I'm mirroring the one that's there. And so this is the exhaust that comes up and out the other pipe. So maybe when you come back to lab, I'll let you take this apart and you can spin it. See how nice and easily that spins? And it's variable speed. So this varies the speed. It goes from 1500 to 4700 RPMs. Well, 4,700 is quite a lot. That's 4,700 times that this would spin around in a full circle. So it has a capability of moving a lot of air. And so however amount of air we're exhausting, we have to pull in the same amount. So a fan doesn't produce air, it just moves it. All right. So what does this look like on the other side? This tends to be a mystery. If you'll see, you can see inside of here. And you should be able to see, let's see, it should be our secondary heat exchanger. And as I back out, this seals against that. It's sealed right there, and it's bolted on. And this is our exhaust pipe, and our inlet is right here. This is basically, think of this as our inlet pipe, and it goes through all the other pipes and eventually goes through here and from our intake. Okay, so it goes just like this, and this is the suction side of the fan. What you can't see, what's very difficult to see, is there's a smoke box right here. This is one that I took off, and this adapter basically mounts to this rectangular piece. And these two tubes, I'll show you here. Here's a secondary heat exchanger, and when I shined my GoPro in, it looked just like that. Everything is pitched down. This is a drain. So as our secondary heat exchanger extracts that last 10 to 15% of energy out of our combustion process, the water will drain out of this drain tube right here. This is nothing more than a drain. If you look at the other side, there it is. It drains any water. This does not hold water typically. It all drains out. And this is what? Anybody have a guess? Guess? Please guess. That's where our pressure switch line is connected to. And so if you think about it, all of this is sealed up. We're measuring right here. Okay, here's our drain. This is our pressure switch line. And it's basically measuring if you look at, that would be, so it's reading full suction off that draft inducer fan. So when our draft inducer is mounted like that, and it's exhausting out, this is proving that this is working. Here's another angle. I'll give you another angle. So when this is on there and this fires up, our pressure switch is right here, and that's proving that this is working. Because internally this smoke box right here, basically plastic, and it's open from the inlet of the fan to that pressure switch opening. Hopefully everybody understands how that works. Now you might be asking yourself, what is a pressure switch? How does that work? What does that do? Pressure switches. A lot of students get very confused on these. So right here, so right now let's just think of one pressure switch. There's two right here, but let's just take it one piece at a time. Let's just think of these as one. It's one pressure switch. So right there is our drain line that I showed you, and has a tube hooked up. Water goes out, and there's a trap. It eventually goes to this trap, and that drains out this line. Okay, it drains away. So we're going to talk about this pressure switch. There's actually two pressure switches. But let's break this down. Let's look at one pressure switch. Think of it as one right now. See on this kind of grayish side, and then you've got this black side. There's two inputs. Got my little pointer. So I don't know if you can see it, but there's a little minus sign right there. If you look over here, there's a plus sign. And what this does is it reads a differential. So there's a higher pressure and a lower pressure. These are the inputs to this pressure switch. And internally, the two sides are separated by a diaphragm. That's what that looks like. And I hooked a line up to you, and I'm gonna just put a little positive pressure on this, the side with the plus, and I'll show you what that diaphragm looks like when there's pressure on it. And I let off again. There's again. So that's positive pressure pushes up against that diaphragm. I'll show you what a negative pressure would look like. So internally, these lines that are hooked up to our pressure switches are imparting pressure against our diaphragm. And on the other side of this diaphragm, I've kind of got a cutaway here. I'll try to get it in my viewfinder. If you see that little plastic tab sticking up, that's connected to the center of the diaphragm. I get this. Little reddish colored plastic tab. So as that diaphragm goes up and down, it's going to impart pressure against those two little brass pieces, which will make and break a set of contacts. So when I look at this pressure switch, based on my pressure differential between the minus and the plus, there's a switch inside of here that's going to either make or break depending on the pressure setting. So this is what that looks like. I took this out of another unit. And it tells you what the pressure setting is supposed to be. So right there. It says 1.05 inches of water column. And this is for the high. It's another setting, 1.76 inches of water column. The reason why we have two pressure switches is because this runs at a high and a high and low fire setting. So on low fire, we don't need nearly as much combustion air. In fact, we don't want too much combustion air because it can actually affect our flame in a bad way, because imagine like a matchstick and you blow across it and you can actually blow it out. So we want to run this, we want to move enough air to provide perfect combustion, or as close to perfect as we can get. And then when we go to high fire, this is going to ramp up, and we need to prove that it's going at the higher speed, moving more combustion air. So on low fire, we need to prove that it's working. And then when it moves to high fire, we're going to prove that this is moving more air. It's based on the pressure differential across this switch. So if you look at the input line, goes up to our pressure switches. There's one input and there's two switches, because internally these are connected. Okay, these are connected. So whatever pressure this is reading, oh, the little thing broke off. But whatever pressure this is reading, it reads it on both sides. And likewise, there's an external line on this one that connects the other side, the positive side. And if I trace that out, it'll just vent up and out. Anyways, this goes to right there. So it's reading the burner side of our heat exchanger. So there's actually a pressure drop across that heat exchanger. So there's more suction here because there's losses inside as you pull through all those little tubes and all that stuff, and through the primary and secondary heat exchanger, there's loss. So this is actually reading a pressure drop from here to here. There's a pressure differential from where our burners are to where the suction side of this is, and that's what this is reading. So on low fire, we want to be at 1.05 inches of water column, and at high fire, we want to be at least 1.75. And I'll show you how we can measure that. Pull that off. So what I did was I put a T in, and I'm just teeing that in. That's all it is. Where this line is, there's a T, and we're connected to the pressure switch. So the pressure switch is still going to work. And then our manometer is also in that line. Hopefully everybody can see and understand what I did there. And so we're going to read this. So it's reading 2.6 inches of water column. So that's the differential from here to here. So we'll go back. The more restrictive a line is, the more losses you're going to have. See, our fire's going. We're on high fire right now. And so that's how we read that. And if I measure my pressure switch, right now my pressure switch should be closed. So I'm going to put this on volts AC. It's a 24 volt power source. I'm going to read across this. And I'm reading 0. I'll show you what that looks like on the board. So if this is my draft inducer, that would be behind it. So it's pulling from here, and this is where my pressure switch is. And that little plastic line goes up to my pressure switch. I'll draw that little smoke box. So I have a drain line, and then right about there is where my pressure switch is hooked up. Now that little plastic tube goes up to a pressure switch with a diaphragm in it. And so there's an input line. And that black tube essentially is going up to where our burners are. So if you visualize this, our burners are up here, and our pressure switch is reading the differential from this smoke box to this smoke box. Because internally, it's going through the secondary and the primary heat exchanger in order to get to there. So we'll take it a step further. So this pressure switch, this has a diaphragm in it, and it's going to make and break a set of contacts. So as this diaphragm moves, it's going to impart pressure on a set of contacts internally. And so there's a normally open, it would be drawn like that, a normally open set of contacts, goes down to our control board, goes somewhere on our control board, doesn't matter where right now, and it goes like that. As that pressure changes, it actuates that switch and closes it. So it's just a path. There's no load on this circuit. The load, everything is internally done digitally in the control board. Okay, all we're concerned about is that this is an electrical path. And it's done to prove that our inducer is working properly and we have the proper amount of airflow. That's why when I have this set to volts, okay, it's considered 24 volts even though it read 26. I have that voltage went up through this switch and back to my control board. If that switch was open, when I read across that switch, it would have read what? It would have given me that 26 volts. But since it was closed, my switch was made, it was, because it's up and running, it's working. When I read across that, it read 0 volts. Because there's no voltage drop across that switch. If you remember from David's electrical class, An electrical meter reads a differential in voltage. It reads the place of highest resistance. So when I go across a closed switch, it'll read 0. Let's go back over. So I showed you what it looks like electrically. I'll take away the electrical side. Where I had my manometer, let's talk about that for a second. So I've got my digital manometer, and there's a negative and a plus pressure. And so all I did was I put a T in here, and I continued it on to my pressure switch. All I did is put a T, and then the other side of the T goes like this. And that hose is connected. So it's open from here. It's open to the pressure switch, and it's also open to my meter. That's what I did. So whatever this is producing, negative pressure, I'm going to read it on here. On my digital manometer, it'll actually read that pressure. All right, so that's how a pressure switch works. If you have any questions, I'd be happy to answer them. Have a nice day.